Thank you, Eric. So I'm going to talk about finding shortest non-trivial cycles in surfaces. Thanks to Saul, I need to make one correction to a question that I answered yesterday about computing things with hyperbolic geometry. The right way to do hyperbolic geometry computations is not by doing hyperbolic trig functions, but rather by reducing everything to the right set of 2x2 integer matrices. So the story that I told yesterday about, oh my God, you have to compute cinches and coches, that's not right. You can actually do the stuff that Dane's algorithm does using 2x2 integer matrices, and you do get almost as efficient an algorithm. But there's some nasty details in the pre-processing, and there's some precision issues in the actual computation. So the resulting algorithm can be implemented, but it won't be as fast. So before I go on, let me correct yesterday. Thank you, Saul. Okay, so shortest non-trivial cycles. So the question that I want to talk about today is this one. I'm given a surface, and I want to find the shortest topologically non-trivial cycle in that surface. Now, as usual, I need to define my terms. Given a surface, you can probably guess what I'm going to be doing. But what do I mean by topologically non-trivial? There are two types of non-triviality that I'm interested in. A surface cycle is contractible if it's homeomorphic to a constant cycle, down to a cycle that just sits at one point. So this cycle over here in red is contractible, but the other two cycles, as we saw in the previous talk, are not. But the other somewhat weaker condition is that we say that a cycle is separating or null homologous if cutting the surface along that cycle breaks it into two pieces. So the cycle in the middle is separating because it separates one handle from the other. The cycle on the right is separating because it separates a disk from everything else. The cycle on the left is non-separating. Every contractible cycle is separating, but not vice versa, because homotopy is a refinement of homology. But this is the picture you should keep in your head. Now, there are lots of reasons within the mathematical literature to be interested in this sort of thing, but the reason that I started doing this, and in fact the reason that I started doing computational topology at all, was motivated by questions in computer graphics back at the turn of the century, the 21st century. So in particular, there was a long spate of results on reconstructing surfaces from point clouds. You take some physical object that you want to digitize and you stick it in a scanner, and you get this amorphous cloud of points, and then you run that point cloud through an algorithm and you get a geometric model. At the time, at least, the standard was a collection of triangles glued together along edges that reconstructs the physical object. The problem here is, I mean, there are interesting mathematical problems built into the second step, but one significant and unavoidable problem is in the first step. You take physical measurements of anything, there will be errors. There will be places on the surface that you can't see. There will be measurement errors. There'll be cosmic rays that hit the scanner. Someone will flash their watch through the laser beam, and you'll get stray points. And the measurement errors typically manifest themselves in the reconstructed surface not only as geometric noise. So if you zoom in here, you see things look a little bit bumpy. That's not the really scary part. The really scary part is the algorithms tend to introduce topology into the surface that's not really there. Okay? And the industry standard algorithms at the time for doing surface simplification largely were based around the idea of contracting edges. Really powerful results of Michael Garland back in the early 2000s sort of set up the theory for this. But the problem is when you just contract an edge, you reduce the number of triangles by 2, but you don't change the topology. It's sort of built into the design of the simplification algorithm that the topology of the surface stays the same. And so the actual example is here is an object that in the real world has, I don't know, genus 3, 4. But when it was reconstructed by the algorithms at the time, the model had genus over 100. And so when you try to simplify it, you always have genus at least 100. And so if you set a target number of vertices, because I want to look at the Buddha from a mile away, I don't need the full resolution, those little interesting little features tend to eat up vertices, and so you get much cruder results. Said differently, if you want to reduce it as much as you possibly can, there's a limit just from Euler's formula on how far you can reduce the complexity of the model. And so what you'd like to be able to do is identify those transient, noisy, not really there topological features and get rid of them so that you can get much more accurate and much more efficient approximations for the reconstructed surface. So this is the reason that I started getting into this, but as I said, these notions are known within the mathematics community by a couple of different names. Geometric topologists think of the length of the shortest non-contractible cycle as something called the systole. This was studied in particular by Gromov in the mid-'80s. People who work in topological graph theory, graph minors, and so on refer to exactly the same object as representativity. This is just now I have a graph that I embed on a surface, and I want to know what the length of its shortest cycle is. And there are interesting results, like if I have a graph embedded on a surface of any genus whose representativity is at least 6, then it's 4-colorable. Or 5-colorable. And then later, Mohar and Thomason did something similar, calling it edge width. Again, exactly the same idea. And then in retrospect, this is a first step in lots and lots and lots and lots and lots of other topological graph algorithms. So yesterday, briefly, I referred to work that Eric and I did on finding shortest homotopic cycles. This is step 1 of that algorithm for building the decomposition of the surface. It also has later been generalized to other settings, not just surfaces, but coverage of the plane by balls based on an abstract model of sensor networks, or the ideas that come and this reappear in more complicated, higher dimensional applications of topological data analysis when needing to compute, again, topological noise. The tools in these later applications are somewhat different, but they still build on some of the same intuition, same ideas. Okay, so as expected, I'm going to start by specifying my input as a surface map, and again, only for purposes of simplifying the talk, I'm going to assume that the surface map is orientable and has no boundary. And I'm going to use n to mean the total complexity of the map and g to mean the genus of the underlying surface. And I'm also going to assume that every edge has a length, which is just some non-negative number. I'm not assuming anything else. There are no coordinates. It's not sitting in space. I don't even necessarily satisfy the triangle inequality, just like yesterday. And then what I want is to find the minimum length cycle in the graph, among the vertices and edges, that is either non-contractible or non-separating. And there'll be two slightly different algorithms, but they'll both be built on the same ideas. Now, when I was originally building the slides for this talk, I was far too ambitious. And so I have a chunk of slides, which I'm not going to be able to talk about, on why am I not, I think actually it was Saul who asked me this question about a decade ago, why am I not solving the real problem? Why am I only dealing with discrete surfaces and paths on edges? And the short answer is because this is all we actually know how to do. But there has been some interchange of ideas between the discrete setting and the continuous setting. So in particular, let me use this as an opportunity to advertise some of my colleagues' work. There's been long-standing work in the geometric topology community on systolic inequalities. Given a Riemannian manifold with two manifold with certain area and negative curvature, what you can prove bounds on the length of the shortest non-contractible cycle. So Gromov showed that every Riemannian surface with area A in genus G has to have a non-contractible cycle of length at most square root of A over G times log G, which is a bizarre looking function, but actually makes sense when you walk through the proof. I should say the constants here, I've just simplified the constants so that the inequalities would be true. These are not the actual constants, but I didn't want to crowd the slide. And for many years, it was a long-standing open problem what the right bound was for discrete surfaces. But by doing a transfer of geometries between the Riemannian and the discrete setting, Colin de Verdier, Hubbard, de Mesme were able to derive a similar tight upper and lower bound. I'll have to defer to them for the technical details here. The main ideas are, if I've got a discrete triangulation, just pretend every triangle is equilateral, smooth it a little. And if I've got a continuous surface, throw down a dense set of points and compute a Delaunay triangulation or Voronoi diagram, and that discretizes it. And then you get inequalities back and forth. Okay? So this is as much as I'm qualified to say about the continuous world, because I'm not that smart. So let me go back to the discrete world. So we've already seen a couple of instances of decompositions by graphs into primal spanning trees and dual spanning trees. And of course, this is the first hammer that I hit everything with. But I want to start by showing you some interesting structures that you can derive from tree-cotree decompositions that turn out to be useful in lots of different applications, not just the one that I'm going to talk about here. To remind you what a tree-cotree decomposition is, given the graph on the surface, you can pick out any spanning tree that you want, any subgraph that touches every vertex and has no cycles and is connected. Then in the dual graph, you can pick out any spanning tree of the edges you haven't already used. And then finally, by Euler's formula, there'll be exactly 2 G edges left over. Okay. Lots and lots of different choices how to do this. But let me now use this structure to derive other things. So one thing that you can trace back to early work on development of the fundamental group and early work in the graph theory literature on looking at cycle spaces is the notion of a fundamental cycle or fundamental loop. So these are very slightly different. So let's pick your favorite spanning tree. In fact, I don't really need the rest of the decomposition. And pick a vertex and call it the base point. A fundamental loop is what you get when you add any non-tree edge to the tree. And then you start at the base point x. You walk to one end of the non-tree edge, across the non-tree edge, and then back to x. There's exactly one loop like this that isn't just a spike, and it's the one that goes through this edge. That's a fundamental loop. Or you can forget about the base point, just put the edge in, and that creates exactly one cycle when you add an edge to a tree. That's called the fundamental cycle. The difference between a fundamental cycle and a fundamental loop is a fundamental loop tends to have a stem. It looks like a balloon with a string attached. You traverse the string up around the balloon and back down the string. The fundamental cycle just doesn't have the string. Okay? So what can we do with these things? If you take all of the fundamental loops determined by the leftover edges in a tree-cotree decomposition, you get a system of loops. You get a set of loops that do two equivalent properties. One, if you cut along these loops, you decompose the surface into a disk. If you prefer to think about this algebraically, you can use these loops as generators of the fundamental group of the surface. Now, the picture, this is exactly the same picture that I used for Dane's algorithm before. In that setting, I actually contracted the spanning tree down to a point, and these loops were single edges. In this setting, those loops actually are walks in the more complicated graph. So only the highlighted edges are the ones that are left over. All the other black edges in the picture are actually edges in the spanning tree. Okay, so I'm not changing the graph. I'm just picking out particular walks to build this system. Similarly, if I just take the set of 2G fundamental cycles, this turns out, first of all of the cycles will be simple. I'm sorry, there's a question? Yes. Okay. All right. Every fundamental cycle is simple because you just walk from U through the tree to V and then across. And these 2G simple cycles turn out to be a basis for the first homology group of the surface. I should point out that I have deliberately not drawn the usual canonical system of loops that has, two loops around every handle, and I've deliberately not drawn the canonical homology basis that has two cycles around every handle, because that's not what you're necessarily going to get. You might get it if you're lucky, you might not. Right? In this case, I get a homology basis that happens to have a connected union, but again, that's just a coincidence because of the way I drew the picture. Okay. Another object that you can get is something called a cut graph. So a cut graph is a subgraph of the graph G whose complement on the surface is a disk. Right, so a system of loops, if you take the union of all the loops, that counts as a cut graph, but this is not the only way to get one. In the geometric topology setting, you might have heard of a cut locus of a point. It's like all the places where there's more than one shortest path back to some source point. It's exactly the same thing, just discrete. Okay, so if I take all of the edges in the spanning tree and all of the leftover edges, and I cut along them, the resulting surface is a disk because what I've done is take the faces and glued them together into a connected piece using the edges of the dual spanning tree. And because the dual spanning tree is connected, the leftover surface is also connected. And because dual spanning tree is acyclic, the surface that I get is actually a disk. Now, a cut locus defined this way tends to have lots of hair. It tends to have lots of vertices of degree 1, things that are branching off that I haven't drawn in the picture. If you remove all these degree 1 edges, if you shave the cut locus, recursively remove all the hair, then you get what I like to call a reduced cut graph. It's something that looks like the picture on the screen. And if you start at least with your initial graph being a triangle, if you start with your initial graph having every vertex with degree 3, then the cut graph will have this combinatorial structure. It'll be a subgraph composed of paths. There'll be exactly 3G of them by Euler's formula, meeting at vertices of degree 3, and there'll be exactly 2G of them by Euler's formula, connected by paths, simple paths inside the graph on the surface. If I've drawn the picture correctly, if you remove the 2G leftover edges, the rest of the cut locus should fall apart into a tree. Yes?
Is this
generically, these statements are true in the smooth setting as well. But generically, because it's possible, if your initial graph doesn't have degree 3 vertices everywhere, you may have a single branch point with degree 8, where lots of paths meet, and then you'll have fewer paths to compensate. Same in the smooth setting. If you've got some degeneracy in your metric, then you may have coincidences like this. Okay? Sometimes you want to build these things by considering the tree and leftover edges and playing around with them. Sometimes it's actually much more convenient to think about the dual graph, and you construct a dual system of loops or a dual system of cycles, or taking it back to the original graph, a system of cocycles. Or I want to build a dual cut graph. And whether you want to do these things in the primal graph or the dual graph is largely a matter of convenience. Because, you know, from an algebraic standpoint, you know, the dual graph's on the same surface. So things are contractible in one if they're contractible in the other. Things are homologous in one if they're cohomologous in the other. It's all equivalent. So for purposes of finding non-trivial cycles, the conditions that we need for these structures are that these are necessary conditions. If I have any non-contractible cycle in the surface anywhere at all, not necessarily the shortest one, it must cross any cut graph at least once. Because if you take the complement of the cut graph, it's a disk. And any cycle that sits inside that disk is contractible, because every cycle in a disk is contractible. And it doesn't matter whether I construct the cut graph in the primal graph, in the primal or in the dual, I still get the same characterization. On the other hand, if I want to do something more weaker and just think about non-separating cycles, then this is the same as having non-trivial homology, and so every cycle that has non-trivial homology must cross at least one cycle in any homology basis, or at least one cocycle in any cohomology basis. And so any non-separating cycle must cross at least one of this system of cycles at least once. Okay. And these are the two main properties that we're going to eventually use in our algorithm. Okay, so this is all preface. This is all, if this is all you remember, tree-cotree is useful for doing graph algorithms on surfaces, I've already won. Okay, now let me be a bit more specific about finding short non-trivial things. So the first algorithmic result for finding these short cycles that I'm aware of is due to Karsten Thomason. It was published in 1990, which is a little embarrassing that I didn't find anything 150 years older. But Thomason observed what he called the three-path condition. If you take any 2 points on the surface and find any 3 paths between those 2 points. And Thomason observed that if 2 of the 3 cycles determined by these 3-point paths are trivial, then the third one must also be trivial. Okay, so I have the red-green cycle and the green-blue cycle. If those are both contractible, then the red-blue cycle is also contractible. If those 2 cycles are both null homologous, or separating, then the red-blue cycle is also going to be null homologous. It's sort of obvious if you think about it. You know, you're used to doing topology, but actually phrasing it this way is really useful because it allows us to characterize shortest things. Specifically, the shortest non-trivial cycle of either type must consist of 2 shortest paths between any pair of points that are as far apart as possible on the cycle. So take your shortest non-contrivial cycle, pick any point, pick another point that's as far away on the cycle as possible. This breaks the cycle into 2 paths. those must be the shortest, globally shortest paths between those two antipodal points, because if they weren't, I could take the true shortest path, say the red and blue thing is I claim the shortest non-contractible cycle, but the red and blue paths are not shortest. Then if I take the green cycle that's the true shortest path, at least one of the other two cycles must be non-contractible by the three-path condition. And it would be shorter because green is shorter than both red and blue. Okay? So these shortest cycles have this very rigid geometry to them that, that pick any two opposite points on the cycle. The two paths they break into are tied for the shortest path between those 2 points. This allows us to actually do a reasonable search instead of wandering around the space of all possible cycles. So, how do we do this? Of course, I have shortest paths here. I already know tree-cotree decompositions, so I'm going to put them together. So I claim that if you're going to build a tree-cotree decomposition, this is the one you should build. Okay, even if it's just, well, I don't care, I might as well build this one. But if you do care, this is probably the one you want. Okay, what I call a greedy cotree decomposition. And remember, the tree-cotree decomposition, I have free choice. I can pick any spanning tree that I want. So the one that I want is a tree of shortest paths from some arbitrarily chosen base point x to all of the other vertices. Right? Just find the shortest way to get from x to p, x to q, x to y, x to z, x to poop emoji, whatever you want to call your vertices. That forms a tree. That's your spanning tree of the graph. Now the spanning cotree is a little bit more subtle. So every non-tree edge, every edge that's not in T, gives you a fundamental loop. I can compute the length of that loop reasonably fast. And I'm going to use the length of that loop as a weight of the corresponding dual edge. And then it turns out the right thing to do is to compute the maximum spanning tree, the heaviest weighted spanning tree of the dual with respect to those weights. It turns out that automatically this dual spanning tree will be disjoint from the shortest path tree that you started with. And by being somewhat clever about how you compute these edge weights, you need to do a little bit of graph algorithms. And by using textbook algorithms for computing shortest path trees and maximum spanning trees, you can build this, this particular greedy cotree decomposition in n log n time. If you really want to be clever, you can actually bring that down to linear time in a couple of special cases. So in particular, if you don't really have weights on the edges, then the shortest path tree is just breadth first search. The maximum spanning tree in the dual is still non-trivial to talk about, but you can still do it in linear time. And even if you do have edge weights, as long as the genus is not too big, by graph algorithms magic, you can get rid of that log factor. Okay, so from now on, I'm just going to call this n log n. The details make an interesting lecture in a different class, but I'm not going to tell them to you here. Okay, so if you want to build the tree-cotree decomposition, if you're writing code to do this, you might as well write the code to do it this way. Okay. Now, why is this what we want? So, in 2005, Sarah Herr-Pellet and I found the following algorithm to construct the shortest non-trivial loop through a given point. So pick a base point x. I want to find the shortest non-something or other loop through that point x. In both types of something or other, we have the same basic algorithm. I start by building the greedy cotree decomposition because I know the three-path condition tells me shortest paths are going to be interesting, so let me build the shortest path tree. and then the maximum spanning tree turns out to be the appropriate dual structure. Then I use that tree-cotree decomposition to build a cut graph in the dual, and then I shave the dual cut graph to get a picture that looks like this. So in this case, because I'm building the cut graph in the dual, it's convenient to assume that my original input graph is a triangulation so that all the dual vertices have degree 3. And so the cut graph actually does look like this. Now, the three-path condition implies that the loop that I'm looking for is going to contain shortest paths from the base point out to some other point on as far away as possible. And that other point is going to be in the middle of some edge, generally. And the edge that it's in the middle of is not going to be an edge in the shortest path tree, because there'll be a shortest way to get to one endpoint and a shortest way to get to the other endpoint, and then I'll kind of meet in the middle. That's where the antipodal point is going to be. So the shortest nontrivial loop is going to be one of these fundamental loops for an edge that's not in the shortest path tree. And then we had a much more complicated argument for this in our paper, but this was simplified by Sergio Cabello, Eric, and Francis Lazarus, that you can actually test very quickly whether a given fundamental loop is non-trivial. So if the edge that you use to create that non-trivial loop is an edge in this dual reduced cut graph, then the loop that you get will be non-contractible because it crosses a cut locus exactly once. And more conversely, if it doesn't cross that reduced cut graph, it's contractible because it's sitting inside a disk. Similarly, or more strongly, you get something that's, so here's an illustration for the separating case. This is a slightly different structure for the cut graph. The loop is non-separating.
Do you mean the loop or the cycle?
I mean the loop. I just haven't drawn it's true for both.
Okay, fine.
It's true for both. It's the loop is non-separating if, moreover, if when I delete the edge that I use to define the fundamental loop, it's an edge of the this dual reduced cut graph. But when I delete that edge, the rest of the cut graph is still connected. So if you look at the red cycle over here, I know that it's non-contractible because it crosses the cut locus. I know that the green cycle is non-contractible because it crosses the cut locus. And moreover, it's always going to cross it at most once because it's shortest. But the green cycle I know is separating because it cuts through a bridge in the cut locus. If I remove that point of intersection, the cut locus falls apart into two pieces. You should think of the cut graph as like a deformation retract of the surface minus the base point. And so if I disconnect the deformation retract, then I'm disconnecting the surface. Okay? So this gives us an easy way of characterizing whether a given fundamental loop has the right topology. The three-path condition means if we want to find the shortest loop that's non-trivial loop through a single point, I just look at every edge in the reduced cut locus and check each one for how long it is. That gives me the shortest non-contractible one. And I do some pre-processing to find all the bridges in the cut locus, and I avoid those, and that will find the shortest non-separating loop. Okay?
You're finding the bottom of the length spectrum, I guess. Can you find like the first K elements simultaneously?
I don't know, actually.
Yeah, because you wanted to do all the way to one.
Right. So the question is, can I find further elements in the length spectrum? So what I do know how to do is I know how to find, for example, the shortest system of loops, so the shortest homology basis. What I don't know how to do is to find the second or third best homotopy class, the second or third best homology class. This is likely to start needing to talk about algorithms for finding second and third and fourth shortest paths in graphs, which are somewhat complicated. I think the further things in the length spectrum are not going to be found as easily as this. But I do think there's some hope that by exploiting these more complicated graph algorithms, you could find something. I'm sorry?
Like maybe you have some quality, you want to find everything shorter than that quality.
Yeah, again, I mean, this is going to require more complicated graph algorithms in addition to more interesting topology. The question was, if you want to find all locally minimal, all cycles that are short in their own homotopy class, but with length less than some threshold, then yeah, I think in principle you could do it, but we don't know the details. Yeah?
Can you do this on a pair of pants?
So this is interesting. So the question is, can we compute pairs of pants? We can compute a pants decomposition. That we know how to do relatively easily using, you know, it's a little bit more complicated than what I'm describing here, but, you know, Eric and I described, in fact, a way of building a canonical structured pair of pants. The question, given a surface graph, can I compute the shortest, a minimum length pants decomposition?
No, I think the question was, what else? But that's an interesting question.
Okay, so I'll finish the sentence. That problem is completely open. It's obviously decidable. We don't know whether there's a polynomial time algorithm. We don't know whether it's NP hard. We don't have any approximation algorithms.
And by minimal length, you mean
The sum of the lengths of the cycles that build the pants decomposition. Okay, that's not the question that you were asking, so what was the question?
That's also something I'm interested in, so that's great.
Okay,
No,
but
my question is if you actually have a pair of pants, so, and now you look for the shortest non-trivial curve on a pair of
if your surface is a pair of pants, okay. Finding the shortest, okay, in this case it's somewhat easier, so if you want the shortest non-trivial cycle, it's going to be homotopic to one of the boundaries.
the one that's not that.
The one that,
Shortest one that's not bound, that's not.
oh, the shortest one that is not, so this is starting to get complicated because that cycle is not going to be simple. But probably by looking at you know, a finite collection of covering spaces and looking for the shortest cycles in those, you might be able to do something. It's an interesting question, but I don't know. Yes?
Since finding the non-trivial loops is equivalent to compute intersection,
It's equivalent to computing what? I'm sorry?
intersection with the dual graph.
It's related, at least. I mean, there's a condition that
I mean, non-trivial loops seems to be minimal in, it seems to intersect minimally the dual graph.
yes. So each of these non-trivial loops intersects this dual cut graph exactly once. If it intersected fewer times, it would be trivial. So you are minimizing an intersection in some sense with this greedy dual structure. Okay, so if you just implement this algorithm carefully for a given base point, constructing the greedy structures takes n log n time, and then you just spend constant time on every edge, seeing which one gives you the shortest loop. That takes n log n time altogether, and if you want to find the shortest loop where you don't specify a base point, or you want to find the shortest cycle, you just try all possible base points. Unfortunately, this is the fastest algorithm we know that doesn't have any dependence on the genus. And there is some circumstantial evidence, at least, to believe you really can't do much better. So there's been a recent trend in the theoretical computer science community looking at what people call fine-grained complexity, where similar to proving problems are NP-hard, if I know that this problem is NP-hard, it doesn't mean formally that we know there's no fast algorithm. It just means if there's a fast algorithm for this, that implies there's a fast algorithm for 10,000 other things that no one knows fast algorithms for. There's a similar statement here. If you could substantially increase the running time of that algorithm below n squared, it would imply that you could improve a long-standing open problem in graph algorithms. Just ignore the surface and find me the shortest cycle in a graph. This is called the girth of a graph. There's a long-standing algorithm back to the 1970s to compute the girth of a graph. It's basically a homework exercise. And this is the fastest algorithm that we know. And if you, and now I'm stretching a little bit and waving my hands. So we would improve algorithms for finding the girth of a sparse graph, meaning the number of edges is not much more than the number of vertices. If you look at the problem of finding the girth of a dense graph, meaning many, a quadratic number of edges, here there are conditional lower bounds due to Virginia and Ryan Williams that say, well, if you could do this in significantly subcubic time, then you could compute all pair shortest paths quickly. You could do Boolean matrix multiplication quickly. You could do all sorts of other things that are bottlenecks in other algorithms would suddenly become faster, and no one knows how to do any of those other things. So there's, as far as I know, no actual conditional lower bound known for finding the girth of a sparse graph, but it smells enough like other things where they have conditional lower bounds that it suggests beating n squared here is going to be difficult, if not impossible. This is one of the frustrating things about theoretical computer science. We brag about making things easy. We talk about developing algorithms, and we're happy when we get algorithms that are faster and faster. We'd like to be able to make unconditional statements about certain things being hard. That you can't solve this problem in less than n squared time. You can't solve this problem in polynomial time. But nobody knows how to prove that anything is hard, because we don't know how to reason about the space of all possible algorithms. It's just, we don't have the intellectual tools to do this. And so theoretical computer science is full of all these conditional claims that says, well, this is almost certainly, morally, you should believe this is hard, because if I can do this quicker, then I can do those other 1,000 things that people have been studying for decades quicker, and nobody believes they can do that either. We prefer to believe that we just haven't found the proof of hardness than that we're all collectively too stupid to come up with faster algorithms.
That means we're stupid one way or the other.
Yes. Right. But we prefer to believe that we're too stupid to come up with an argument that deals with all possible algorithms than to believe that we're stupid for not being able to come up with one.
What is the field called when you're doing reduction in terms of algorithm complexity instead of, like, usually computational complexity, NP, reduction?
So it's usually called fine-grained complexity.
Fine-grained complexity.
Yeah. Okay. But it turns out that if you're interested in surfaces with small genus, I mean, this hardness result, if it's a result, would really only apply when the genus is very large. When the genus is very small, we can do better, and this is what I want to spend the next half hour or so doing, 20, 35 minutes. We'll see how far I actually get. So there's you can think of this as a corollary of the three-path condition, which I like to refer to as the one-crossing condition. If I look at the shortest non-trivial cycle, and I look at any shortest path between any two vertices in the surface, those two objects cross either once or not at all. So when I look at this picture, I can immediately conclude that one of two things is true. Either that green cycle is not the shortest non-contractible cycle, or that red path is not the shortest path between its two endpoints, because those two objects cross more than once. Right? It's quite possible that red thing is the shortest path because I just got some weird lengths on the edges. But in that case, I know the green cycle isn't optimal. And similarly, I know that the blue cycle isn't optimal because of this one crossing condition. So Cabello and Mohar took this one crossing condition and combined it with this fact about non-separating cycles crossing any system, any homology basis. And they observed that the shortest non-separating cycle, on the one hand, must cross at least one cycle in a greedy system at least once.
Sorry, could you just show the bottom of the slide? Yes, okay.
Okay. So it must cross at least one cycle in any system of cycles at least once. But on the other hand, if I take a greedy system of cycles, the shortest non-separating cycle crosses each cycle in that system at most once. Okay? So I have a greater than and I have a less than. And so in principle now I can speed up the search for a non-separating cycle by saying, well, let's compute the greedy system of cycles using the tree-cotree decompositions. And here I'm doing this in the primal graph, not in the dual. That's this thing in blue. And then for each of the blue cycles, find the shortest cycle in the graph that crosses that blue cycle exactly once. Whatever the shortest cycle that crosses each of these things exactly once, the shortest of all of those will be the shortest non-separating cycle in my graph. So how do I find, now I've reduced the question now to pick out one of the cycles in this basis, and I want to find the shortest cycle in a graph that crosses that cycle exactly one time. And so the way to do this is actually to do surgery on the surface. I'm going to take the cycle that I want to cross exactly once, and I cut the surface open. And now what I want to find is a shortest path between the two clones of the same vertex that used to be on that common cycle. So for every vertex in one copy of the cycle, I want to find the shortest path to the corresponding vertex in the other copy of the cycle. And I need to do this for every vertex on that cycle. Now, if I do this naively, I haven't actually sped anything up. But at this point, I pull out a hammer from the graph algorithms literature that actually lets me do this search faster than just saying compute a shortest path at this point, compute a shortest path at this point, compute a shortest path at this point, which is called the multiple source shortest path problem. The picture will make sense in about 15 minutes. If you haven't seen the YouTube channel, the Slow-Mo guys, hi Dan, hi Gav, go watch it, it's cool. They see all sorts of things exploding and breaking and so on at many thousands of frames per second. It's mindless, it's fun, go watch. What's the multiple source shortest path problem? So when I cut the surface open along that cycle, I create two new faces in a surface with genus that's lower by one. I'm really only going to pay attention to one of them. And the problem more generally that I'm trying to solve is I have a bunch of pairs of vertices that I want to compute shortest paths between, with the property that one vertex in every pair is on that one face that I've picked out. So maybe I want to compute this shortest path, and this shortest path, and this shortest path, and this shortest path. But in every case, one end of the shortest path is on that face. And let's think of that face as being the boundary of the surface. That face is actually missing. So of course I can just run a standard textbook shortest path algorithm from every vertex on that face, and well, that face might actually have a constant fraction of the vertices on its boundary, so this doesn't actually speed anything up. But it turns out that as long as I'm happy with some implicit representation of all those distances, I can actually compute all of those shortest path trees in only near linear time when the genus is fixed. And this is the magic of Philip Klein. Phil Klein is a professor at Brown who is the wizard of planar graphs. He came up with this multiple source shortest path thing in the context of planar graphs, which I need to spend some time on to get some of the ideas across. And it really has been incredibly influential in lots of other algorithms, not only in this topological setting, but it's basically been fostered a revolution in the development of planar graph algorithms. So I'm gonna advertise a little bit of planar graph algorithms. At this point, those of you who are mathematicians are going to start getting a little bit uncomfortable because I'm switching to an algorithms lecture. I'm really going to be doing algorithms now. And so again, like I did yesterday, I really want to encourage you to stop me and ask questions at any time, because I'm going to be talking about things that computer scientists are completely comfortable with, we hope, but which may be unfamiliar if you haven't taken an algorithms class. So I'm going to start with a graph in the plane. There's no topology here. But this will get the main ideas across. Okay, there's the Jordan curve theorem. That ultimately is the only topology we'll use, is the Jordan curve theorem. Yes, I'm sorry.
On the previous slide, what was the G in that computational complexity there?
It's the genus of the underlying surface. And as usual in time bounds like this, when G is 0, pretend it's 1. Okay. So again, I want to compute a bunch of shortest paths, each with one endpoint on the boundary and one endpoint somewhere else. And intuitively, what we want to compute is the shortest path tree rooted at every vertex on the boundary of the graph. Okay? I want to compute all these trees. And each of these trees has complexity n, and there might be n of them, depending on how many vertices are on the outside. And so it looks like we're computing n squared things. But in fact, we don't need to compute each of these things explicitly. What we need to compute is just compute the initial shortest path tree, and then for the later shortest path trees, only compute the changes from the previous shortest path tree. So this may be gone by a little bit fast, but the blue edges, if you focus on a blue arrow, you'll notice it doesn't change. It's the blue arrows are the ones that didn't change from the previous tree. I only need to compute the red ones. These are the ones that are being introduced as a new edge in a tree at every stage. So we're going to be doing this, okay? And now, okay, so I'm going to write down the initial tree, and I'm going to write down the changes for the later trees. And I want to try to convince you that this is only a linear amount of information that I'm writing down. And the proof of this is going to boil down to what I call the disk tree lemma, because it almost doesn't deserve to be called the lemma, because it's an easy consequence of the Jordan curve theorem. But if you take any tree embedded on a disk and you pick your favorite edge and you delete it, and this breaks the tree into two smaller trees, color one of them red, color the other one blue. There are either 0 or 2 intervals on the boundary of the disk that have one red endpoint and one blue endpoint. Okay? So if I delete this edge, I get that. If I, delete that edge, I get some red thing over there. If I delete this thing, I get some red thing over there. If I had, for example, deleted this edge here in the middle, maybe the red subtree would only consist of that one vertex floating in the middle, and then I wouldn't have any red-blue intervals on the boundary. So that's the 0 case. But if there are any red-blue things on the boundary, then there are exactly 2 of them. And this is, the Jordan curve theorem, because basically what I'm saying is I can take a disk around the red subtree, and it will intersect the boundary of the disk in an interesting way only twice. Okay, so with this lemma in hand, I can bound the number of times that an edge will pivot into the tree, the number of times that I need to introduce a new edge into the tree to replace some other edge. And to do this analysis, let me focus on a particular edge, x to y, and consider the tree of shortest paths ending at y. Okay? Now, a particular vertex on the boundary will include the edge xy in its shortest path tree if and only if the shortest path from S to Y goes through X, which means that path shows up in the subtree of this tree rooted at X. Okay? So I'm thinking about the shortest path tree rooted at X, and then I'm thinking about the reverse subtree, shortest path tree rooted at Y, and if there's a path from S to Y, that path shows up in both trees. And so in both trees, either that path contains the edge from X to Y or it doesn't. So all of the sources whose shortest path trees include X to Y, these are precisely the vertices on the boundary in this subtree of the shortest path tree rooted at Y, into Y. But by the disk-tree lemma, this means that as I move the source vertex around the disk, there is exactly one place where I start using the edge xy, and there's exactly one place where I stop using the edge xy. So when I'm writing down this list of changes, there is exactly one point in that list where I say, now start using edge xy, and there's exactly one point where I say, stop using xy. And by Euler's formula, there's a linear number of edges in the graph, and so there are a linear number of changes overall, and so I only need to write down a linear number of pieces of information. So the thing I'm computing, the initial tree plus the changes, this really is only order n stuff. And so it's reasonable to expect that I might be able to compute it in something like order n time. Of course, now the devil's in the details. How do you actually find these pivots? How do you actually determine which edges pivot in and which edges pivot out? Phil had one way to do this, and then later Sergio, Aaron, and I developed a different way of doing this, which I think is a little bit cleaner. Phil's since adopted our method, so yay. There's a long series of papers that is best summarized as read Phil Klein's papers, fail to understand the proof, develop my own proof, notice that it either is or isn't the same as Phil's proof. If it isn't, publish a paper. So I need to divert a little bit away even further into doing an algorithms class. I need to tell you how shortest path algorithms work. Welcome to sophomore level algorithms. Okay, so the input here is I have a graph, I have weights on the edges, and what I want to compute when I want to compute shortest paths is I want to compute a distance at every node, and I want to compute a predecessor for every node that gives me the tree structure. Okay? So all shortest path algorithms maintain this information, where in the middle of the algorithm, the distance value isn't the length of the shortest path until the end, but it's the length of some path from S to V. And the predecessor is the last, it tells you the last edge of some path from S to V. And so in the middle of an algorithm, I might have a tree that looks like this, where the numbers inside the nodes are the distances, and the blue arrows pointing into the nodes, those indicate the predecessors. Now, if you stare at this picture for very few seconds, you might think, how do I know that this is not the shortest path tree? Yeah? The 7 in the middle is wrong. And the way that you can tell the 7 in the middle is wrong is actually not by examining the whole graph. You just need to look at that one edge there in the middle. And you'll notice that this edge is what Lester Ford in the 1950s called, this edge is tense. This edge certifies that I don't have the correct shortest path distances. The distance at the end is bigger than the distance at the beginning plus the length of the edge. As long as you have a tense edge somewhere in your graph, you don't have the final shortest path distances. Your algorithm is wrong. And the thing that Ford observed is that if I want to compute shortest path distances, the following strategy is enough. Initialize all the distances to infinity except the distance at the source to be 0. Then as long as there is a tense edge, relax it. That's the algorithm. That is every shortest path algorithm. That is Bellman-Ford, that is Dijkstra, that is Floyd-Warshall. That is every algorithm basically is built on this idea. Find a tense edge and relax it. Find another tense edge and relax it. Find another tense edge and relax it. Now notice when in a general shortest path algorithm, when I relax one edge, it may cause other edges to be tense. Fine, so this will propagate for a while. But eventually you reach a state where none of the edges are tense, and at that point you know you have the shortest path algorithm. You have the correct shortest paths. If you're familiar with optimization, you may have noticed something. I defined shortest paths by a process that makes things smaller and smaller and smaller. It's a bit weird that I'm looking for the largest distances that satisfy this no tenseness condition. What you're seeing is an example of linear programming duality at work, and that's actually how Ford developed this. If you don't know what I just said, let it wash over you. Don't worry about it. So how do we exploit Ford's characterization of shortest paths in our multiple shortest path algorithms? So, I'm sorry, there's a question?
Yeah. How do we know that we don't get stuck with local minimum? Not that familiar with optimization like this.
There's a lovely proof by induction,
Okay.
which I don't want to tell you. So what I'm going to do is I'm going to pretend for just a moment to be not a discrete computer scientist, but a continuous person. And I'm going to use a trick that is shown up in several other places in computational geometry, where I'm going to maintain the shortest path tree as the source moves around the outer boundary of my graph, but as it moves continuously. So I'm going to drag the source vertex across, and the distances are all going to change continuously, but the structure of the tree is only going to change at certain critical moments. And it's those certain critical moments that I really need to find. As I move the source point around, I'm going to maintain all of the distances, but I'm also going to maintain this quantity called the slack for all the edges that are not in the tree. This is how much the edge doesn't care that it's in the shortest path tree. As soon as if the slack of any edge is negative, this is Ford's condition that the edge is tense. Okay? So distances and slacks change as I drag the edge. And as long as none of the slacks drop below 0, I'm happy. The distances are changing, but the structure is not. I have the correct predecessors. So give you an intuitive picture of what's going on. As I move the source vertex continuously from U to V at speed 1, all of the distances in the blue subtree are decreasing at rate 1. And all of the distances in the red subtree are increasing at rate 1. But the slacks in those edges are not changing. They're fixed. Any edge in the shortest path tree has slack 0. The edges that are not in the shortest path tree that I'm interested in. The edges that have both red endpoints, both of the distances on either end are increasing, and so the difference in those distances is not changing, so the slack is constant. Same for an edge that has 2 blue endpoints. If a directed edge goes from a red vertex to a blue vertex, then that means the distance at the back of the edge is going up and the distance at the front of the edge is going down. It's less and less interesting to think about that edge. The slack is increasing. But if I have a directed edge from blue to red, those are the ones where the slack is going down. And this is where I have to pay a little bit of attention. These I'll refer to as the active edges in the graph. Now, if one of these edges, the slack is going down, if the slack ever reaches 0, then I know I have to do something, because if I go any further, the tree is going to be wrong. Now, there's a nice characterization of these active edges by looking at the dual spanning tree. Tree-cotree, it's the only hammer I have. So if I look at the dual spanning tree, the complementary spanning tree here, there is a unique path that connects, that separates the red edges from the blue edges. In terms of like Whitney's duality between cuts and cycles, if I just remove the edge UV from my primal graph, that separates the tree into two parts. There's a unique cycle in the dual graph that separates those two parts, and this is most of that cycle. So every active edge is dual to an edge on this particular path from the face on one side of UV to the face on the other side of UV. And so if I want to find which edge is going to become tense first, I only need to pay attention to the edges dual to this path. Okay? Now, when that happens, what do I need to do? I say, okay, look, I've discovered that green arrow, that edge, that's the first one whose slack is going to go to 0. So I move the source to the point where it actually goes to 0. And then I need to do some surgery on the trees. So I need to add that edge, which is about to become tense, to the shortest path tree. So I do a relaxation. I add that edge. That means that the predecessor of that red vertex on the right needs to change to the blue on the left, needs to change to the blue vertex on the right. So I add the new edge that's about to become tense into the shortest path tree, and I remove the edge that used to point into the same vertex. This one. Okay, so I do a pivot. But now I also need to update the dual spanning tree, and I do exactly the opposite. The edge that I added to the shortest path tree I remove from the dual, and the edge I remove from the primal I add to the dual. And now I have a new path that I need to check for the next active edge. And this is the set of new active edges. And so the last thing to observe here is that I don't do any redundant pivots. The pivots that I do are exactly the things that I need to do to change the shortest path tree rooted at U into the shortest path tree rooted at V, because once a vertex changes from blue to red to blue, it never changes again. Once I pivot an edge in, its color changes, and colors can only change in one direction. So this is roughly what the process looks like. As I slide from left to right, I find tense edges and I pivot them in, and this tree slowly evolves from being mostly red to being mostly blue. And now I have to pull out the big hammers and just point. So how do I do all this stuff efficiently? I've got trees and I'm looking at paths, and you'll notice actually here when I pivot the edge into the tree, that whole subtree changed from the whole subtree changed from red to blue. So I'm doing things to the spanning tree, the shortest path tree, that involve subtrees. I'm doing things in the dual spanning tree that involve paths. I'm updating distances. So how do I do that quickly? Well, there's this lovely data structure developed by Bob Tarjan and his various students, Danny Slater in particular, that allows me to maintain these trees in a data structure that lets me do subtree operations and lets me do path operations in log n time. Totally not the context for this. I'll just point, if you're interested, to this book. Actually, the Tarjan-Wernick paper in SOTA 2005 is quite readable. But this can all be done quickly. And so what this means is that I can execute these order n pivots in a total of n log n time. And as I'm executing the pivots, when I notice that I've computed the distance that I need, I can look it up in the data structures in log n time. And so I can compute in n log n plus k log n time any k distances that I want where one endpoint is on the boundary. Okay. But that was in the plane. We don't care about shortest non-trivial cycles in the plane because there aren't any. So we have to now pop back up. So in the higher genus setting, we're doing more or less the same thing. Again, we've got an outer boundary face, and we want to compute shortest paths from that outer boundary face to a bunch of other places. We're going to do exactly the same thing. We're going to move the source continuously around that outer boundary face and maintain the shortest path tree. Again, using this tree-cotree decomposition to guide where we look for searches. So I'll very briefly give you the high-level sketch of what's different. The first thing is that the complementary dual subgraph, what you get when you delete the spanning tree and look in the dual, is no longer a spanning tree. It's got these extra edges. Aaron and Sergio and I came up with a different way of decomposing that dual cut graph that isn't just a tree plus 2G extra edges. We reduce down to the reduced dual cut graph, and for each of these paths with hair hanging off of it, we break that path off and all the trees hanging out of it into a separate tree. And so we get what we call a grove decomposition. So we get a collection of 6G subtrees that cover everything. And then why is this interesting? Because if you look at the dual reduced cut graph, there's some red stuff on the left and some blue stuff on the right, and the green stuff in the middle, the active edges all lie dual to some of these cut paths. And so instead of searching this one path through the dual graph, we might need to search order G different paths in the dual structure. Having this grove decomposition, you do more complicated data structure stuff to maintain it. So that's on the data structure side, but then there was also the analysis side. We bounded the number of pivots by essentially invoking the Jordan curve theorem. We don't have the Jordan curve theorem anymore, so how do we bound the number of pivots? Well, it turns out that the number of pivots is upper bounded by the maximum number of non-homotopic simple paths, disjoint simple paths, between one point and on the surface and the boundary face. This is exactly the same number of paths that you get in a system of quads that we use for Dane's algorithm. So it turns out to be exactly 4G, right? So every edge could pivot into the shortest path tree at most 4G times. And so the total number of pivots is only order Gn instead of order n. And then we do some further data structure magic to take the order G penalty that we get from the grove decomposition and the order G penalty we get from the number of pivots, and we can get rid of one of the G's. And nasty, nasty details. But the punchline is we can compute implicitly all of these distances in about Gn log n time with some technical caveats. So there's some high probability results there which we can get rid of because we need to assume shortest paths are unique. There's a slide. We're getting way down in the weeds at this point, so I really need to pop back up. Okay, but this particular algorithm that really proved to be very useful for us in lots of different contexts, lots of different algorithms for building structures and finding structures in surface graphs and doing optimization of other kinds in surface graphs, really rely on this multiple shortest path tool as a hammer. So we're happy that we were able to figure this out. So if I continuing to pop back up the stack, yes, Matthias.
One question, this multiple shortest path, I mean, it seems to, I mean, is there anything which prevents it to work in high dimensions? I mean,
Well, we don't have tree-cotree decompositions in higher dimensions. So I'm not sure what you mean by it as soon as you go to higher dimensions. Right. There may be a way to make something work, but I'm not sure what it would be. Certainly, I mean, in the primal setting, you'd have a tree, but maintaining the dual structure and reasoning about the dual structure and searching the dual structure, I think would be much more difficult.
So, I mean, the general problem would be what is the curve of a graph? Right, like you could always take your manifold, approximate it by some very dense one skeleton, and then say, okay, what's the difference?
Yeah.
And that's
Okay. Yes.
Do you think that these algorithms can be really implemented in practice?
Yes. and I do think it can be implemented in practice because it has been implemented. Now, the place where you don't want to implement it is the fancy data structures that give you log-in time. That will add, ridiculous amounts of overhead. One thing that Phil Klein has done in particular is shown that if the edges of the graph are unweighted, you really only need to put 2 fingers into the graph and maintain them very, very carefully, and then everything works in linear time. And then my student, Kyle Fox, and I, and another student at Illinois, we were able to generalize that with some pain to higher genus surfaces. So there's one set of constant factor overhead from the data structures which you really want to avoid because it's not really necessary in practice. There's a bit more constant overhead because every one of those pivots involves doing 6 different things. So the constants are not great, but at least in the planar setting, actually it works blazingly fast if you just implement it right. Okay, so let me finish this one last set of 2 or 3 slides and then I'll let you go. So remember, what we needed to do to find the shortest non-separating cycle is find the shortest path from any vertex on this cycle to its clone on the other side. And the multiple shortest path algorithm lets us do this in gn log n time. And so if we just do that once for every cycle in the greedy system of cycles, we get an algorithm that runs in g squared n log n time, at least with high probability details. And this is actually the fastest algorithm we know, both in terms of n and g. Maybe you could shave off one of those g's by working really hard, but again, there are these fine-grained complexity reasons to believe you can't get rid of the g's entirely. There's more stuff on finding shortest non-contractible cycles, but I think given the time at this point, I should stop and ask if you guys have any other questions. And thank you for your patience. I realized many of you didn't realize you were signing up for an algorithms lecture. Thanks for listening. Yes, Ben.
So I have a follow-up question on the implementability. So I totally get this concept of having some black boxes that you just avoid because you don't need it in practice. But
Right.
For the stuff that you do code up, where does it sit on the scale from one person implemented it once and everybody else uses that because it's so much drama, down to every undergrad whoever needs it implements their own version because it's so easy? Where does it sit on that scale?
So I actually had an undergrad doing a senior thesis with me this past semester that he actually coded up his own version of the planar MSSP algorithm, and it took him about a week. Right. So doing the higher genus stuff, I suspect that there's more cognitive overload in understanding what the hell genus is than in building, tree-cotree structures. So the Grove decomposition is a little bit subtle. That might add another week to the implementation, but I think the harder part is actually understanding what is going on than doing the actual implementation. Now, if you want to implement your own self-adjusting top trees, that's going to at least quadruple the implementation time and not really improve the running time significantly. So that's the part where you just want to let other people do that if you want to use it at all. Yeah?
What changes when you have surfaces with boundary?
When you have surfaces with boundary, mostly what changes is now you have 2 different questions that you might ask. One is, how do you find a shortest non-trivial cycle? And the other is, how do you find a shortest non-trivial arc, boundary to boundary path? So the cycle stuff actually goes through with only trivial modifications. The finding shortest non-trivial arcs, essentially, if you know that you're going from one boundary back to the same boundary, you contract that boundary down to a point, and now you're looking for loops. And if you're going between different boundaries, well, then it's never going to be contractible, but it's never going to be separating, so you're just finding shortest paths. But similarly with non-orientable stuff, all of this stuff actually just happens. It just goes through. The finding shortest non-trivial things, for some of them you might need to go up to the oriented double cover, but I don't think so. I think everything just goes through. You just have to change what the, well, G, there's a factor of 2 question how you define G, but it doesn't matter because it's all hidden in the big O.
More questions?
Yes?
Just for the just historic question about the shortest path in the tree. So you didn't mention Dijkstra, so
I cited him at least 5 times.
okay.
So it's, yeah. Of course, the Dijkstra is what you would implement if you want to compute, like even in the MSSP, the first step is build the initial shortest path tree. And that you would use Dijkstra's algorithm.
Okay, thank you.
Okay, thank you.